Have you ever wondered how your radio works? When you turn the knob, then you can change the radio station? Maybe you know that you're changing the frequency. Well, what you're actually doing is you're adjusting the resonant frequency of the circuit. You're adjusting that frequency so that it matches the frequency of the radio station that is broadcasting the music to you. So the radio station broadcasts at a certain frequency, and you're matching that frequency in the circuit. And what is called a resonant frequency of that circuit. So that's what this next section is about. It's about resonance. So a radio has an RLC circuit that is designed to have a particular frequency at which it wants to oscillate. So I always like to make an example of swinging a kid on a swing. Right, so you've got your swing here, and you've got your kid on there, all right? And you're pushing the kid. So the kid is swinging back and forth on the swing, all right? So you know that if you're over here and you're pushing the kid, that you have to push at a certain frequency. So if you push, it goes, come back, push, come back, push, come back, right? If you keep pushing at that frequency, then what happens? The swing gets bigger and bigger if you keep on pushing right at the correct moment. But what if the swing is coming back and you start pushing it at random moments? Then the swing is basically going to stop. It's not going to have a nice big amplitude if you don't push at the correct frequency. So this is what I like to think with resonant frequency. There's a certain frequency in your circuit that allows it to resonate. It allows, in this case, a maximum current to occur in the circuit. You can think of that as the frequency of the push here that allows a maximum amplitude. Think of it that way. So when you tune your radio, you're adjusting the frequency of the circuit to equal that of the station that you want to listen to. So what is this special resonant frequency at which our circuit wants to oscillate, just like our swing wants to oscillate at a certain frequency? What is that frequency? So for our RLC circuits, the frequency occurs when you have a maximum current in your circuit. So if you look at Ohm's law, current is voltage over impedance. If you want to have maximum current, that means you want minimum impedance. So that's what the second bullet says. Well, how does this happen? How do you have minimum impedance? Let's take a look at the equation for impedance. The square root of R squared plus XL minus XC squared. For our impedance to be a minimum, then we want this to equal 0. We want this to cancel out. That will make what's in the square root as small as possible. For this to cancel out to 0, that means that the inductive reactance must equal the capacitive reactance. So that's what I have here. The XC must equal the XL. When XC equals XL, let's see what happens. So let's write down the formulas for XC, which is 1 over 2 pi FC. Let's have that equal to XL, which is 2 pi FL. So there's a special frequency, F, that allows these two to be equal to each other. So let's solve for F. Let's multiply by F on both sides and divide by 2 pi L as well. Let's divide everything by 2 pi. Well, let's do one thing at a time. So let's multiply by F. So we're going to have 1 over 2 pi C equals 2 pi F squared times L. And then let's go ahead and divide by 2 pi L on both sides. I'm going to come over here. If you divide this side by 2 pi L, then it's all going to be in the denominator. 1 over 2 pi C, and now we've divided by 2 pi L, that goes in the denominator as well. And on the right-hand side, we're only left with frequency squared. And then let's go ahead and take the square root of each side to get the f by itself. So see what happens. We've got 2 pi and 2 pi in the denominator. That's the whole quantity 2 pi squared. So when you take the square root, it comes out of the square root sign. So we're going to have 1 over 2 pi. The 2 pi squared comes out of the square root. And inside the square root, we're just left with a c and a l. Or we can put an L and C. That's the only thing that's left under the square root. And we're left with frequency. So this is a special frequency that allows the reactances to equal each other, which allows the impedance to be a minimum, which allows the current to be a max. So we call this special frequency, we call it the resonant frequency. F sub 0, that's the resonant frequency of our circuit. Let's take a look at one your turn question, and then we'll have one example. If the value of R is increased, what happens to the resonant frequency? Well, we just learned the equation for resonant frequency. 1 over 2 pi square root of LC. The resonant frequency does not depend on the value of resistance. There's no R anywhere. So there's no impact. It stays the same. R does not affect the resonant frequency. Only the capacitance and the inductance. Let's do one example. Back to our radio. So we have a local radio station, transmits at a frequency of 94.3 megahertz. The tuning circuit of a car radio consists of a 1 Henry inductor in series with a variable capacitor. So we have our circuit, we have an AC circuit. It's going to resonate at a certain frequency. The inductance is fixed, but by turning the knob, what you're doing is you're changing the capacitance. And what you're doing is you're changing this capacitance, which is changing the resonant frequency of the circuit. And it allows that particular frequency to be transmitted, to be broadcasted, if you tune it to that frequency. So you have to adjust it to the right capacitance to get the right frequency. So what we're doing here is we're solving for C in our equation. So there's a little bit of algebra here to get the capacitance by itself. So first thing, I would multiply both sides by the square root of LC to get it out of the denominator. So FO square root of LC equals 1 over 2 pi. Get rid of that term in the denominator here, that factor. And then we can divide by the frequency to get rid of that. So square root of LC equals 1 over 2 pi F. Now we can square both sides. What's going to happen, and I have more room down here, but I'll just finish it up here. So when we square both sides, we get rid of the square root here. We get L times C, and we get 1 over, and then we have 2 squared, pi squared, and FO squared. So 4 pi squared, FO squared. And then divide by L to get C by itself. So C equals 1 over 4 pi squared, FO squared, L. That's the value of capacitance, and then we plug and chug our numbers in there. So 4 pi squared, and we know that we want the resonant frequency to match the frequency of the radio station. So 94.3 times 10 to the 6. And then we want the inductance is 1 Henry here times 1. So plug all of that in, and when you do, don't forget to square the frequency here. And then when you plug all of that in, then you'll get 2.85 times 10 to the negative 18 farads for the capacitance, and you can now listen to your radio station. So that's all, folks. I hope that you enjoyed it.